Hello everyone, this is Mr. Williams again. Thanks for joining me on this little mini lesson. And today's mini lesson is on significant figures and calculations. And what we want to make sure that we first understand is what a significant figure actually is. Remember, significant figures and measurements are the values of the known digits to the limit of the calibration of the measurement plus one estimated digit beyond that limit of calibration. That's the digit that's normally forgotten when taking measurements. This is important because you're only as good with a measurement as the device being used to measure or make that measurement. And so, for example, if we're trying to measure volumes of liquid, maybe you only need 400 milliliters as an approximation to heat a flask or a test tube. In that case, you could use a beaker because their graduations, there aren't that many of them. They may be 50 or 100 milliliters in between and aren't really good for measuring, but they give an approximation. But if you wanted to measure density or maybe amounts with titrations, you want to use a graduated cylinder to the 1/10 of a milliliter or maybe a burette to the 100th of a milliliter, depending on what you're looking for and what calculations you're trying to make with it. Those two different measuring tools give better and more significant digits in their measurements, and thus they actually cost more too. So let's take a look at significant figures. There are three rules that we need to talk about when identifying the number of significant figures within a measurement. First off, always remember that non-zero integers are always significant. For example, if we went back to a balance and we measured 45 point, let's say 18 grams on the balance, and that is the number. First off, that 8 is an estimated on those electronic top-loading balances, and so you see sometimes that it will flicker back and forth. But since they are all non-zero, we're going to record all four significant figures in that measurement. We actually have some balances that work even better than that. For example, we may have 12.1177 grams on one of our analytical balances, and if you notice, that balance can actually give 6 significant figures in that measurement, 2 more than the top loader, and thus, depending on what we were working with, is a much better choice for our measurements. The big rule is rule number 2, which deals with zeros, and there are a couple of parts to zeros because there's 3 kinds of zeros. First, there are leading zeros in a measurement, and the leading zeros will precede the non-zero digits. They're not considered significant. For example, if we took 0.00127 milliliters, in that measurement, those zeros are not in the measurement itself. If we wrote that in scientific notation, you would write 1.27 times 10 to the minus third milliliters for an example, and those zeros go away. So anytime you have zeros that are in front of a non-zero digit, they are not considered significant, and there would only be 3. The second part are your captured zeros. Captured zeros are zeros that lie in between non-zero digits. Those digits are always significant. For example, if you had 505 meters as a measurement. In this case, we know that the 5 and the second 5 are both significant because they are non-zero digits. I like to think of this as the goalpost rule a little bit because I can make a couple of little lines on my 0. It looks like a football. I draw a line between those 2 arrows. The kick is up. It is good. And so therefore that is a significant number, and there would be 3 significant digits in that measurement. It wouldn't make a difference how many zeros you had at a time. For example, 4,001 grams. There would actually be 4 significant figures because both those zeros lie in between non-zero digits. The third type of zero is a trailing zero, and those are the ones that follow significant digits and follow the non-zero digits. And as long as they contain a decimal point, you can consider them significant. Again, let's go back to our balance example. If we had, let's say, 23.10 grams measured on the balance, you measured 4 significant figures in that case. That hundredths place of the measurement was measured, it just happens to be a 0. So since it is after the numbers and after the decimal point, it is a significant digit. The question becomes is what happens when there are zeros on the left-hand side of your decimal point. For example, is there a difference between 500 meters and 500 with a decimal point meters? And the answer is there actually is. In the first example, there is no decimal point. Those zeros right here and here act as placeholders, and they give an approximate distance. For example, from my classroom to the stadium, it's about 500 meters. And so there's only really one significant figure in that measurement, because I'm plus or minus 100 meters in that measurement or estimation. The second one, though, the 500 with the decimal point, both of these zeros then become significant, and there are 3 significant figures because that decimal point indicates that it was measured. Now, every now and then you'll come across a calculation, and in that calculation you may get an answer that is, let's say, 50,000 meters squared. And let's say you need to have 3 significant digits in that measurement or in that calculation. Well, we count the 5, 1, 0, 2, 0, 3. We put a line over top. That will indicate that there are 3 significant figures because that last 0 is significant. But the other 2 that trail, these 2 do not. We cannot add a decimal point because if we added a decimal point, that would have indicated that there were 5 instead of the 3 that actually are. So that's a little review of significant figures. Let's talk about calculating with them, because that's what we're going to do enough. Well, first off, exact numbers do not count in significant figure calculations because they're exact numbers, like Avogadro's number. 6.02 times 10 to the 23rd has an infinite number of significant figures for what we would need. All right, now let's talk about calculating. Sorry about that. So we can either add or subtract measurements with significant digits. And when we do that, the answer of an addition or subtraction problem must contain the same number of digits that is in the common place of all of the measurements. For example, if I took 3.46 meters and I would try to add that with 12.2 meters. Initially I do the addition and I get 15.66 meters, but that cannot be my final answer. The reason is that the last common place of my measurements is the tenths place. And since this 6 is greater than 5, it will cause that 6 to round, and our answer would be 15.7 meters for that specific problem. Subtraction works the exact same way. If we had 415.22 grams, and we were trying to subtract 113 grams from that initial measurement, we'd get an answer of 302.22 grams. Again, the last common place in this example happens to be the ones place. The 2 is less than 5, so it will not cause that to round, and our final answer is 302 grams for that problem. It's good to know these rules for addition and subtraction. You will see them in some cases maybe when calculating averages, but most of the time we spend a lot of time calculating with multiplication and division. And the answers to a multiplication and division problem can only have the same number of significant figures as the measurement with the least number of significant figures. And in that case, it doesn't matter where the decimal place is in either of the numbers that your measurements that you're multiplying or dividing, or in your answer, you just have to count up the number of significant figures and keep it to the least. For example, let's say I tried to take 4.75 meters times 112.6 meters. In this case, when you first do the multiplication, you get 534.85 meters squared as a calculator answer. But that can't be our final answer because there's more significant figures than in our measurements, and we're only as good as our least accurate measurement. In the case of the first measurement, there are 3 significant figures. In the second measurement, there are 4. So since the smaller number is 3, we must round this to 3. That would cause 1, 2, 3. The 8 causes the 4 to round, and an answer would be 535 meters squared. Division works the same way. If we were to take something like 11.87 meters squared, and we were to divide that by 79.935 meters, in this case, when you get an answer, it actually is really long on your calculator. It is 0.14849 5, 6, 5, and so on. And it goes on for a couple of more digits. Well, that number looks really exact if we were to include all of those non-zero digits. But since the first measurement has 4 and our second measurement has 5 significant figures, we can only use 4 in our final answer. And so that would be 0.148. The 9 causes the 4 to round to a 5. Our unit, meters squared divided by meters, is meters. And that is our final answer. Now, some students ask, isn't that 0 right here significant? Well, if you remember, that's a leading 0 before non-zero digits, and we know from a little earlier in this presentation that it is not significant. What I have for you now are some practice problems. All right, so what I'd like you to do is try those practice problems. In a moment or two, I will put up the answers, and you can check to see if you were right. I hope this little mini lesson has helped you in learning about significant figures.